Having seen the components involved in calculating the takeoff distance, let's now look at how these are changed, and more importantly, how the takeoff distance changes given different factors. The first of these is the effect of increasing mass. Increasing mass has several significant effects on the takeoff. The first is that a greater amount of mass for a given force will reduce the acceleration because it is harder to move a heavier object. This is the effect of inertia. We can see this effect in this part of the formula. So therefore, the takeoff distance will increase. A second effect of mass is that there will be more load on the wheels, and therefore wheel drag will increase. Again, this effect will increase the takeoff distance. The third effect is not as apparent as the others. A heavier aircraft will require more lift in order to get airborne. To get this lift, the aircraft will need to travel faster and will require a higher takeoff speed. Getting to this higher speed will require a greater distance, and therefore the takeoff distance will increase. The last effect is that a higher mass will reduce the aircraft's angle in the initial climb. This decreased angle will increase the airborne distance to get to 50 feet, as shown. A rough calculation to help you quickly quantify the effect is to know that a 10% increase in mass will increase the takeoff distance by approximately 20%, or a factor of 1.2. The next factor to discuss that will affect the takeoff is the air density. This has three effects. The first is that a reduced density will reduce the thrust. This is because not as much air, and therefore not as much oxygen, enters the engine for combustion. This will reduce the acceleration force and as a result increase the takeoff distance. The second effect of a reduced density is to do with the takeoff speed. A reduction in density will increase the true airspeed for any given indicated airspeed. To attain the same indicated airspeed, which is a function of dynamic pressure, the aircraft needs to travel faster through the air. This means that the aircraft's true takeoff speed is higher, and as a result, the takeoff distance will be greater. The third effect that density has on the takeoff distance is that it will reduce the angle of the initial climb, and as already mentioned, this will increase the airborne distance to get to 50 feet. We must be aware of what causes low density and therefore low aircraft performance. A useful statement to memorize is that high, hot or humid conditions all decrease air density and aircraft performance. A rough calculation you can use is to remember that for every 1,000 feet increase in altitude or 10 degrees centigrade increase in temperature, the takeoff distance will increase by approximately 10%, or a factor of 1.1. All aircraft will get airborne at a certain indicated airspeed or dynamic pressure. However, if there is a headwind of 20 knots, then a stationary aircraft will already be experiencing dynamic pressure and register an indicated airspeed of 20 knots, yet the aircraft ground speed is 0. So the aircraft is already closer to its flying speed even though it is not yet moving. So, headwinds will reduce the ground speed for any given indicated airspeed and consequently reduce your takeoff distance. Tailwinds will increase your ground speed for any given indicated airspeed and increase your takeoff distance. An additional effect that wind will have is on the angle of the initial climb. Headwinds will tend to increase the climb angle and reduce the takeoff distance, whereas tailwinds will reduce the angle and increase the takeoff distance. When using winds, it is recommended that you do not use the actual wind that is given, just in case when you actually get airborne the wind changes and thus your takeoff distance changes. When calculating takeoff distances, the recommendation is that you use 50% of the headwind component and 150% of the tailwind component. As an example, if the wind were reported to be 10 knots of headwind, only use 50% of this, which is 5 knots. Most performance graphs that calculate the takeoff distance have this recommendation already applied. The example shown here includes this. You will notice it because of the different slopes of the headwind and tailwind lines. Tailwinds have a greater effect on the distance than headwinds. Slope has an impact on the takeoff distance because it affects how the component of weight acts along the longitudinal axis of the aircraft. Notice here that a stationary aircraft on a level runway has weight acting straight down towards the centre of the Earth. However, when the aircraft is on an upslope, the weight still acts towards the centre of the Earth, but there is a component of weight, shown here, which acts in the direction of drag, that is, backwards along the longitudinal axis. This will reduce the acceleration and increase your takeoff distance. Conversely, when the aircraft is on a downslope, the weight component now acts in the direction of thrust. This will increase the acceleration and decrease your takeoff distance. A rough calculation to help you quickly quantify the effect of slopes is to assume that for every 1% slope, the takeoff distance is affected by 5% or a factor of 1.05. Most takeoff performance graphs assume a paved hard surface. If conditions of the runway are not like this, then the effect on takeoff distance needs to be understood and corrections applied. A lot of small airfields have grass runways. The grass will increase the drag on the wheels, or in other words, increase the rolling resistance. This will reduce the acceleration and as a result increase the takeoff distance. A wet runway, whether grass or paved, will have a similar effect and increase the drag on the wheels, and hence increase the takeoff distance. There are approximate calculations to help you calculate the effect. Dry grass up to 20 centimetres will increase the takeoff distance by 20% or a factor of 1.2. However, wet grass will have an even greater effect, and it will increase the takeoff distance by 30% or by a factor of 1.3. If the ground is very soft or there is snow, then the takeoff distance will increase by approximately 25%, which is a factor of 1.25. Do not attempt to take off in grass more than 25 centimeters long, or if there is slush on the runway. The reason is that the wheel drag may be so high that the acceleration will be insufficient to get the aircraft to a flying speed. Flaps are trailing edge devices used to increase the camber of the wing and generate more lift, thereby reducing the stalling speed. However, a lot of flap will dramatically increase drag as well. Let's take a look at how different flap angles can affect the takeoff distance. With no flap, the aircraft will accelerate and then climb to the screen height as shown. However, with some flaps selected, more lift will be generated and the aircraft will get airborne at a slower speed. This can be as much as 10 knots less than without any flaps. However, with flaps, a small penalty is paid in the fact that the initial climb angle is shallower. Nevertheless, the overall effect is that the takeoff distance reduces. If too much flap is used in the takeoff, then the wing will generate more drag than lift. The result of that would be that the acceleration is reduced and the takeoff distance increases compared to a no-flap takeoff. Too much flap would also significantly reduce the initial climb angle, exacerbating the effect. However, the effect of flap varies significantly from one aircraft to another. Some aircraft require the use of flaps for takeoff, whilst some don't. Familiarise yourself with your aircraft and use the flap settings laid down by the manufacturer in the aircraft manual. There are many other factors which need consideration when calculating your takeoff distance. These include the use of differential braking when trying to maintain directional control in strong crosswinds. Other considerations include wind shear and turbulence, as well as contamination on the aircraft itself, such as ice, snow or rain, and low tyre pressure, which will increase rolling resistance.